and welcome friends. I am glad that you have joined this course on defects in crystalline solids. So, as it says part 1, because this is a little extensive course, so it has been divided into two 20 lecture courses and this is first part of it. I am hoping that you have gone through the intro lecture, that was the intro video that is posted on the course website. I am Professor Shashank Shekhar. I am a professor in material science engineering at IIT Kanpur. Okay, so let us get going with a brief introduction to this particular course. Let us start with what are defects. We are talking about defects in crystalline materials. Okay, so defects can be of many kind. It can be related to non-structures also, it can be related to topography, it can be related to many other aspects, defects in many other aspects, but when we are talking about defects in this particular course, we are talking about defects with respect to crystallinity. Now, what do we mean by defects in crystallinity? Defects in crystallinity or crystalline system is whenever you get a discontinuity in crystalline periodicity. So, this discontinuity can be of various kinds. As you will see, it can be that just one atom is missing or a row of atom is missing, or maybe that there are all the atoms present, but one of the atoms is of bigger size. That is also a discontinuity now, because the atoms around it will have to adjust. So, these are all different kinds of defects and all of them will have influence on the properties. So, what are the examples? So, let us look at some examples that we encounter with respect to defects. Here are a very wide variety of list, and this has been classified based on dimensions. Okay, so, because we are talking about crystalline, so crystalline materials, so it is a very good classification with respect to dimensions. When we talk about 0 dimension, it is something related with atoms or one point lattice defect. So, examples for 0 dimensions would be vacancy, when you have a missing atom, impurity, when you have an atom present which is not supposed to be there, which for example, if you add in copper there is some antimony present, then that will be an impurity. Frankel defect. Frankel defect is when lattice ion moves to interstitial. Now, to maintain charge neutrality, it will always happen that these will always take place in pairs. So, there will be anionic as well as cationic ions moving into lattice sites, interstitial sites. So, that is also a Frankel defect, and like I said, since we are talking about anionic and cationic, it means that usually Frankel defects are associated with ceramics or anionic or charged ionic kind of systems. However, you can also define it in a metal. So, whenever an atom moves from its original site to an interstitial, that can also be defined as Frankel, but that is a very mundane definition of Frankel. The real or the more technical or the more accepted Frankel is when you have ions moving into interstitials. Then we have Schottky, vacancies of opposite sides. Now, here both the cations and anions, and again like I said, this is we are talking about cations and anions here, which means we are talking about ionic materials. So, when both cations and anions are missing from the site, meaning vacancy for a cation, vacancy for an anion is present as a pair, then it is called Schottky. It need not be exactly at the same place. Okay, it is just that for maintaining charge neutrality, you would know that on a whole, the vacancy fraction of anions would be equal to vacancy fraction of cations, at least in terms of charge. So, the total charge carried by vacancy anions would be equal to total charge of vacancy cations. Interstitial. Now, this can be defined for a pure material also. When an atom moves away from its site and into the interstitial, that will be a interstitial defect. Now, this can happen because either the material itself has gone into the interstitial site, or another ion or another atom which is forming an alloy with this is going into the interstitial site. In many cases, these kind of defects can exist as a homogeneous alloy. For example, iron carbon alloy. In this iron carbon alloy, carbon is always at the interstitial site. So, this defect is actually present homogeneously in the system and giving it the overall properties different from iron, and we get a steel. Iron carbon is steel. So, this alloy is forming because of this kind of defect. Still another kind of defect, 0D defect, is anti-site. For example, in gallium arsenide, gallium may be sitting at arsenide place, and the arsenide may be sitting at the gallium site. So, this is the wrong atom at the wrong place both, and again this has to occur in pairs. So, this is the anti-site 0D defect, meaning only at point defects. 0D is point defects. Now, let us go to another dimension, which is 1D. So, here row of atoms or row of defect would be formed, and the most common or the most encountered example in this category is dislocations. Now, this dislocation itself, as you would later see in the course, are of two types: screw dislocations and edge dislocations. In both of them, there is a line of atom which is missing, or the structure around it gets changed. So, this is a different kind of defect. Related to dislocation, but very different from dislocation, is disclination. You can think of it as a twist in the crystal. So, this twist will occur around one axis, and that axis defines the line of defect in disclination. So, again this is a 1D defect, and it is very different from dislocation. With dislocations usually have a small range effect, while disclinations have a long range effects. Now, let us move to one dimension higher, and then we get to 2D surface. Now, I said discontinuity in crystalline periodicity is a defect. So, as you can realize that you are moving in from the bulk, when you reach the surface, suddenly the atoms have moved away, there is no more atoms over there. So, this is discontinuity. So, in that sense surface is also a defect, and it is not only in that sense, because even otherwise you would see that all the characteristics that you find for a defect like energy, forces, all these also exist with surface. You have surface energy associated with it. Then because of the presence of this defect, there is relaxation near the atoms, because on one side there are no more push and pull of the atoms, on the other side there is push and pull of the atoms. So, on one side where the atoms are there, they relax. So, that leads to the defect which we will call as surface defects. Interfaces. Now, even inside material single, let us say we are talking about a single element material, let us say copper. Even in a copper, the crystallinity does not extend all the way from one end to another end. Okay. There is a break in periodicity, and these regions of uniform periodicity are called grains, and they are interrupted by grain boundaries or interfaces. So, there are this kind of boundaries which are called homophase boundaries, meaning that two phases which are being separated by this boundary, by this interface, by this plane are same. So, it is a homophase interface or homophase boundaries. The other kind can be interphase. For example, let us talk about duplex steel. Now, here you have two phases, austenite phase as well as the ferrite phase. So, one is BCC, austenite is FCC and ferrite is BCC. Now, whenever there is a boundary between these two, the crystalline structures are different on both the sides, and this kind of boundary which differentiates or which interrupts the continuity is called heterophase boundaries or interphase boundaries. Still another kind of 2D defect in materials is the stacking fault. Now, this stacking fault we will get to know more when we talk about dislocations and particularly the partial dislocations. It is more to do with there is a particular layer by layer arrangement, for example, ABC arrangement that you see in FCC or AB arrangement in HCP. However, if this stacking is interrupted, then or for example, instead of going ABC it goes ABA, then there is a change in the stacking layer, and because of this the nearest neighbor or the next nearest neighbor gets changed, and this leads to increase in energy, and this itself is a defect. So, this stacking fault is also related to partial defects or the partial dislocations in FCC materials. Let us get to the 3D defects. 3D defects are voids. For example, what are voids? When you have culmination of several like you can say vacancies, or in fact missing atoms from one place, then they form void. But these voids are not formed just like that. Sometimes they can be formed because of cluster of vacancies, but they are also formed because of, let us say, plastic deformation. There can be voids getting formed. Another 3D defect is precipitates. So, for example, if you have a material which forms precipitate at certain temperature or certain condition, then this new phase appears as precipitates, and this appearance of a different phase which will have different crystallinity, different properties, this will lead to a change in the continuity of the matrix structure. So, again this is a defect, and this will again in fact in most cases, as we will discuss later, particularly in aluminum system, precipitates are very useful because they impart additional strength to material. Cracks are another defect. So, this is for example, if you have let us say instead of precipitates you have inclusions which are very large in size and which generate large amount of stress in the matrix, then these large amount of stresses can open up or lead to opening of cracks in the material. So, these cracks are also a defect which are 3 dimensional in nature. It will have a very large scale. It is not in the same it is not of the same order as atom or site, it is much larger in that sense, and therefore, it is a 3D defect. Porosity. So, for example, people who work in powder metallurgy, they would know that when you are trying to sinter materials, not each and every region gets filled up, and those regions which do not get filled up are called porosity. So, this is again something like void, but its origin is different and its has a, you can say, very different properties, so leading to different properties, and therefore, they are categorized separately like porosity. So, this is not an exhaustive list. In fact, the list of defects that I have mentioned here, they themselves will have several sub topics under them, and we will not be able to go through all of them, but what we will do is we will be going through some of the important characteristics. And as you would realize that when we are talking about material properties, particularly the mechanical properties, dislocations are the ones which make the most important difference to properties, and therefore, a lot of time would be spent on dislocation. We will also be spending time on vacancies and other kind of defects. However, like I said that a lot of time would be devoted to dislocations and material properties like mechanical behavior that are influenced by these dislocations, and these this will be extended to certain extent to 2D and 3D defects. In the previous slide, we classified defects on the basis of dimensions, but they can also be can be classified on whether they are statistical, something like random. They have to be there just because of for example, point defects, they are thermodynamically stable structures. So, they will be present at a particular temperature in certain quantities. So, they will be statistical defects. So, random dislocations will also be counted in statistical defects. They are homogeneously distributed. Point defects are another ones. Another category in this is whether they are structural defects, whether their presence causes certain particular kind of structural change in the material. So, they are not really homogeneous in that sense. For example, LAGB or low angle grain boundaries, when they are present there, they lead to some geometrical deformation or geometrical change in the orientation. If you have random dislocations, they will not cause any particular orientation change, but when you have low angle grain boundaries, which is a array of dislocation arranged around a certain order or a certain kind, for example, one above the other, then it leads to change in the misorientation between the neighboring parts, and therefore, they are called structural defects. Now, let us get to the topic of why do we need to study defects. Obviously, we have said that it influences properties. So, defect structure plays important role in determining many important properties and phenomena. And the properties and phenomena which are influenced or which are sensitive to defects are called structure sensitive properties and phenomena. So, what are those structure sensitive properties? Like I said, some of the mechanical properties are the most sensitive to structure. For example, strength, the yield strength, and if you remember in mild steel, what is the kind of yield strength or the tensile plot that we get? If you remember, it is let me draw it over here. So, this is a stress strain curve for a mild steel, and why is it like this? We will understand it in more detail later on, but for now let me just tell you that this is because of interaction between point defects and dislocations. So, the dislocations get fixed or pinned because of the presence of point defects, and because of that you need a much larger strength which is called upper yield strength. Now, once this dislocations start to move, then the yield strength of the material drops and we get to lower yield strength. And this band, which is nothing but extension, which is that how much region is getting this mobile dislocation, is called Lode band. And beyond this, once all of the material has uniform dislocation, mobile dislocation, then the material starts to behave in a common way, just like you would expect for any other, let us say, aluminum system, how their yield strength or stress strain curve would vary. As you keep increasing the strain, there will be work hardening, and then you will reach a UTS and so on. So, this is a very good example of how properties get influenced by defects. In fact, even more fundamental to this is that if you had no dislocation present in a material, do you know how much would be its strength? For example, copper yield strength is of the order of 100 megapascal. However, if you were to have a copper material without any defect, do you know how much, can you expect how much strength should be? It would be of the order of 10 gigapascal. So, that is the kind of difference defects make. So, sometimes defect can be useful for you, sometimes defects can be bad for you. So, just imagine a world where we had materials without any dislocations and we would have very high strength material, but fortunately or unfortunately there are dislocations, and because of which the actual strength of these copper materials are so smaller. Fracture toughness is another of those properties which are influenced because of the presence of defects. For example, if there are lots of voids, then the fracture toughness would be much smaller, and you can do fractography to characterize, to understand how many defects were there, what kind of fracture you obtained because of the presence of these defects. Also inclusions can reduce, like I said, inclusions will lead to crack growth. So, that can also reduce fracture toughness. So, all these defects do influence the properties. Now, let us talk about some phenomena. Diffusion, if you have a 2D structure, 2D defect like interface, or a 1D defect like dislocation line, the diffusion is known to be much faster along this region. And why is it? Because the overall volume available around these defects are much larger, and therefore, the atoms find it much easier to migrate or hop around these places. Therefore, diffusion becomes much faster, and in fact, we have diffusivity coefficient for dislocation or diffusivity related to dislocations, diffusivity related to grain boundaries, diffusivity related to triple junctions. Because defects are getting they are all increasing order of defects, where they have you can say increasing amount of volume for atoms to jump, and therefore, the overall diffusion rate becomes faster. These are mostly mechanical and functional properties, but we also have electrical properties like resistance. If you have a lot of defects in a material, then their resistance increases, or in other words its conductance decreases, because a lot of most of these conductivity is taking place because of movement of ions or electrons. In if it is material, if it is the ionic material, then by ions, and if it is other material, then by electrons. Now, if you have lot of defects, then a lot of scattering takes place of these electrons, and because of this the resistance increases, and if we are talking about ionic materials, then their movement gets impeded or mobility decreases, and therefore, again resistance increases or conductance decreases. But there are also certain properties which to you can say a large extent are insensitive to structure, meaning defects will not be able to influence this. One of the most important one is density. So, you may have point defects and you may think that why should our density not decrease. However, the defects that we are talking about are a very small fraction of the total lattice sites present. For all practical purposes, we will never be able to reach a region or a range where you will have significant fraction of point defects, or for that matter any of these line defects, which can increase the overall volume, and therefore, density can be termed as structure insensitive property. Similarly, elastic modulus, it is directly related to the bond strength, and again the fraction of impurity or the fraction of defect that we have added is so small that you would not see any real change in elastic modulus. So, these two properties, these are two examples of properties that can be termed as structure insensitive properties. So, now that we have I have introduced you to the basics of defect, let me bring you to what is the objective of this course, what are the objectives of this course. We hope that at the end of this course you should have a broad understanding of structures of defect, how the defect structure looks like, whether it is we are talking about point defects, line defect, interfaces, or voids, or any of the 3D defects, and their role in determining properties of materials. A thorough understanding of the structure of dislocations in various crystals and their interaction. So, as you will see that when we are talking about this course, we have already said that a large emphasis will be on dislocation, because most of the mechanical properties are influenced by that. So, you must also at the end of this course be able to understand the structure of dislocation in more detail, in a much greater detail, in various crystals and their interaction, and and also their individual properties, not just the interaction, but also their individual properties. And since we are talking about dislocations, so also the overview of how this dislocation influence the overall plastic properties of the material. When we are doing plastic deformation, then how do these defects play a role in that. Now, by the time that you are watching these videos, most likely all these lectures have been recorded, but I would insist, or I will urge you, that whenever you feel that there are certain aspects that you need clarification on, do feel free to contact, and we can always add some tutorial modules at any stage to be able to help you in this. Now, when we say understanding defect structure, what should be the way to go ahead? How do we proceed for this? First, what we need to do is understand isolated defects. So, whether we are talking about vacancies, so how does the vacancy behave when it is present in isolation, meaning the whole crystal system there is only one vacancy. So, first we need to understand isolated defects, understand their stress fields, understand what is their energy, what is their formation, and if it is a charged unit, then what are the charges present on it. Then we get to the next stage. Now we have understood the structure of one unit, how do they interact with in pair. So, let us say we are talking about dislocation or vacancy to vacancy, how do they interact in pair, or maybe how do the point defect or the vacancy interact with the grain boundary. So, these can be termed as short range interactions, meaning that even if you take a real material, then there will be lots and lots of these defects present of different kinds. And when we are talking about pairwise, we are saying how do they at a very small scale, what is the influence of these interactions. For example, what is the influence of this point defect and the dislocation. So, this will give you short range properties or short range interaction behavior. Then this understanding would be extended to understanding behavior of the entire defect structure with external constraints. So, now we have the whole system, there are, let us say there are so many other dislocations present or other point defects present. In that entire system, what is the behavior of this dislocation? For example, dislocation dynamics, how do the dislocations move when there are so many other dislocations present in the region. So, that is the, you can say, path to understanding defect structure. This is the modus operandi that we will follow to understand individual defects. Important descriptors of dislocation. Now, here let me introduce you to some of the important, we have talked about different dimensional dislocations. So, let me introduce you to different kinds of important descriptors of these different dimensions of dislocation. So, let us say we are talking about 0 dimension dislocation. So, let me say this is 0 dimension. So, what is the density of this? You can say rho 0 or rho vacancy. These are usually given in what units? Number per unit volume. So, these are this is just to understand what will be the usual description or the method of description of these defects. So, the units will be per meter cube, and on an average. So, let us say this is spacing. So, what will be the average spacing between this? So, this can be obtained approximate value. We will never be able to say the exact value, because this will be based on other information that you would need, but on an average you can say that if this is rho v is the density, then what will be the average spacing, and average spacing can be termed as rho v to the power minus 1 by 3. So, you take a cube root of the density and in the inverse of the cube root of the density of the vacancies, and that will give you the average spacing. Similarly, you can do it for one dimension. So, in one dimension, let us say we have rho 1, which is equal to we are talking about dislocation. So, I will term it as rho d, and the units here would be, it should be length per unit volume, because it is one dimension. So, this will have unit of meter minus 2, and here the average spacing can be given as rho d to the power minus 1 by 2. So, inverse of square root of dislocation. Similarly, when we go to 2 dimension, which is like a plane or a boundary. So, I will call it rho b. It is now area per unit volume, and therefore, unit will be equal to meter to the power minus 1, and here the average spacing would be equal to 1 over this value. So, we will have minus 1, and these are all units of meter, because we are talking about spacing. However, when we get to 3 dimension defects like voids, then it becomes a little difficult, and for example, let us say void or particle, then here we have volume of particle by volume, and here the unit itself is 0. Now, this is a little bit difficult to find spacing, because let us say we have 20% fraction of one phase. So, this 20% fraction can be distributed in different ways. It can be all in one place, or it can be distributed like very small fractions, and hence the average spacing cannot be obtained from just the information of rho p in any situation, not as a, not even as a average value. So, we cannot sorry, not the rho p, but the average spacing. So, the average spacing between these particles cannot be obtained from this information. So, as you can see that this is one phase, this is second phase, and it can be distributed in different ways, and depending on that the spacing would be different. So, here this will be the spacing, here this will be the spacing. So, here that because of that we will not be able to find the average spacing just based on this information, which is the volume fraction, which is V p by V. Okay, so, this is some important description of dislocation, and before me end this lecture, just an important aspect, what is the big perspective. One must understand that a complete understanding of the defects is still missing. Okay, is a, for example, even a point defect, how they actually affect the structure around it is still a topic of debate, and it is not really 100% understood in all the materials. Therefore, you must keep a big perspective in your mind that what we are studying are simple models to be able to predict some properties and phenomena based on this. So, with that introduction we will come to this end, and next lecture we will start with one of the defects. Thank you.